Yes, very good evening, Rakesh. Very good evening. So, a warm welcome to this first live episode of Learning General Theory of Relativity. A warm welcome. My name is Shaunak, and welcome to my channel, Physics for Students. So, the basic essence of this series, which I am planning to continue, I'm sure I will continue, is to give a more mathematical view of general theory of relativity, keeping into mind certain very deep understanding of relativity, which is otherwise not mentioned in most of the books, textbooks, or in general the popular, videos, etc. So what I would try to do is that this series will continue for class after class. I will be dealing with the mathematics which I have not dealt with videos. Now you might say, sir, why it is not with video? Because you need to understand that video is meant for a certain group of people. Maybe people who are MSc, PhD are also watching. Maybe people who are from class 11, 12 or BSc is watching. But this is an exclusive class. So what happens in a class? A professor goes deep into understanding. So what I will do, the basic idea is to go deep into mathematics. Definitely, I will be going more into tensors, etc., and building up the base. But before that, what I would like to tell today, was to start with this part of this program, that what is a system? Now we need to understand that general theory of relativity, most of the people, you will see that most of the textbooks, any textbooks of general theory of relativity will start with general relativity has got a space-time curvature. Gravity is not a force, it is a space-time curvature, and it directly goes into first into Newton's laws of motions, then Poisson's equation, gravitational potential, tensors. So they start with the mathematics. But what these books, etc., I'm not criticizing, don't take me wrong. What these books, etc., they don't tell is that why and how general theory of relativity is a classical system. Now you might be saying, I know, sir, what is a classical system? Newton's law, thermodynamics, Boltzmann's constant, everything is a classical system. But there is something much more deeper that you need to understand. Because if today you are not understanding, if you take up GR as a special paper, you won't be able to understand it later. So first, I would like to tell you that what is a system. So as you can see here, system actually comes from the Greek word systema or Latin word systema, and it means a collection of objects that are interacting with each other. Now hold on for a minute. This concept of system will be useful for you for two purposes. One is to know the classical macro level of physics, and very importantly, the micro level, that is quantum mechanics. As we say, that until you see the darkness, you cannot enjoy the beauty of light. So until you understand a macroscopic system, you won't be able to enjoy what is called a microscopic or a quantum system, because you never know where your career is leading to. So for example, here you see whole concept made up of several parts. Now, say for example, I have given a ball which is rolling down here. You can see the ball is rolling down. So we can create a simple system consisting of ball and a smooth surface. By studying the system, we can learn about the laws of physics that govern the objects of motion. So it can be as simple as a cricket ball, and it can be as complex like a universe. What is important from this slide, if you're taking a note, if you're writing it down, it is better. Otherwise, you can just watch this line, that it consists of behavior of objects in a controlled environment. Now, what do I mean by controlled environment? What is an uncontrolled environment? That means we are dealing with a system which is very controlled, and there is not much of external interferences. The basic definition of a system. Again, I am telling, if you understand this today clearly, the concept, the underlying, I would say, the basic philosophical concept of quantum mechanics will be much easier. We go to the next part. Now you see, so for example, a rocket, a mechanical system, a thermodynamical system, electrodynamics, a quantum system, these are all systems. Fine, you define a rocket, how it goes above. It allows you to make predictions, that means about the behavior of objects in the real world. Again, please take a close note. allows the behavior of objects in the real world. Does that mean there is something which is an imaginary world? No. What I'm trying to make a point is that real world means the macroscopic world, you and me and everything around this room, and another is the microscopic world. That means this definition of system tells that it makes prediction of the behavior of the real world, that means around me. Now, here is a very fundamental and a very deep question. That means, can we predict the behavior of particles in the quantum system? Definitely we can. But the question now is that in the quantum system, how do we predict the behavior? How does it go? That is the significance, or that is the difference which I'm coming to. Now, you might be wondering, okay, this is a system, everything is system. Which is not a system? Can you tell me? For example, force. Now, forces are fundamental interactions between particles or objects like gravity, electromagnetism, strong force, weak force. But force are not system. Why? Because they are not composed of interactive parts. Force acts on somebody, but they are not composed of small parts. Understand? So force is not a system. Fields are also not a system, because on a field a force is exerted. Electric field, charged particle around a region, right? But fields are not system because it is not composed of interacting parts. That means field itself is not a system. Oh, what happened? Constants of nature, for example, reduced Planck's constant, the speed of light, the gravitational constant. So constants of nature are not system. Why? Because they are not composed of interacting parts. Constants are not interacting. Again, symmetries are physical laws that remains unchanged. For example, laws of physics under symmetric notations. I will be coming in my upcoming webinar on 25th of November, which is on Saturday. I will talk more about system symmetries there. Symmetries are not system because they are not composed of interacting parts. This is very central. I'm not going into general relativity right now. I'm making you understand what is a system. Because if you don't understand a system, you will never understand a quantum system or a macroscopic system. Fine. So I meant to say this, you can just skip. So Sadi Carnot, who was basically the founder of the Carnot system in thermodynamics, then Ludwig von Betelfeny, Austrian biologist who designed system, Norbert Wiener and Ross Ashby cybernetics. Anyway, these are the people who actually, through history, they define what is a system. If you have any question, if you're not being able to understand, please write to me in the chat box. Okay, now in physics, primary there are three types of systems. One is a classical system, which is deterministic. One is a relativistic system, and another is a quantum system, which is a probabilistic. Now hold on, what do I mean by deterministic and probabilistic? You can already gauge. I hope you can understand. But there is something more deeper in that. Let me show you the next part. So here you see that our classical system is defined by Newtonian mechanics, definitely. A relativistic system consists of special and general relativity, which is actually defining the geometry of space-time. And quantum systems are guided by wave function. Now, the basic objective of this part of our today's lesson, I will be telling you, is to prove scientifically that why do we consider general relativity as a classical system. You will say, sir, it's a classical system because it carries momentum, etc. No, I want to go a little bit more deeper and make you understand and prove that why general relativity is considered as a classical system. So it is just like that. Once you understand what is light, you can see how what is darkness. So when you understand, it will serve both purpose, that you understand what is a classical system and general relativity is a classical system, you can very well understand that, okay, so that means what is a quantum system. Okay. So here is a question which I would like to pose to all of you, that do you think that general theory of relativity is all about relativity? I mean to say all the mathematics is about relativity, or there is something else? Let me show you. Now, I think those, maybe Rakesh who knows me, or those who have participated in the webinar, they know it already anyway. So you see what I'm trying to tell over here. Let me first remove this slide. Now you see, special theory of relativity actually consists of these things. It is obviously happening in inertial frame of reference. It deals with speed and velocity. It is experimentally provable, and it has got frames of reference. Very clear, very clear. So that means, you see, in special theory of relativity, below the arrow I have written that it is a study of relativity and simultaneity. That means which frame of reference, which observer is moving, speed, time, space, all those things. Very clear. Now if you see with general theory of relativity, non-inertial frame of reference, it is deals with gravity, it deals with geometry of space-time, and on a large scale. Now here I would like to take a pause and tell to those who are watching me today, maybe you are students, maybe you are MSc or PhD people, but one thing you need to understand right from today's lecture is that how do you understand general relativity? I mean to say, how do you approach general relativity? Is it directly to the mathematics? Is it directly through the equivalence principle? This question will also be answered in today's class. So you see, what I'm trying to tell in this slide is that non-inertial frame, gravity, geometry of space-time, these are all dealing with curvatures. That means we can draw a conclusion that general theory of relativity deals more with geometry and less with relativity. Now, don't get confused that I'm not saying that relativity or mathematics is not there. Definitely, it has got a lot of huge amount of mathematics. But what I'm trying to make you understand is that it does not deal with relativity only. It does not deal with inertial frame, speed, velocity, etc. But it deals with non-inertial frame, gravity, geometry on a very large scale. So that means, my dear students and viewers who are watching now, that means we are now moving into an arena. We are shifting from special relativity and we are moving into geometry. We are moving into curvature. We are moving into non-Euclidean geometry. So from now, can I draw a conclusion that you need to have a better understanding of non-Euclidean geometry, visualization of space-time, but not typically mathematics? So that is why the famous physicist and teacher Neil Turok told that general relativity is more intuitive, quantum mechanics is more mathematical. I hope this will come more clear in today's class. So you see all those things. You are all aware. You know what are those things: space-time, manifold, tensor, Ricci curvature, Christopher Simon, parallel transport, affine connection. Okay. Now what I'm trying to tell is that all of these things, if you intuitively and try to calculate, you will see all these things are more about what you call geometry. You tell me where is Lorentz transformation. You tell me where is time dilation. You tell me where is Lorentz bound. You tell me where is Maxwell's relativistic equation. All these things, which will come clear if you are participating in the 25th November webinar, which is much more detailed, you will see all these are related to what? Geometry. That means you need to have a very good grasp or concept of geometry, not typically mathematics, geometrical mathematics. If you are good in geometry or intuition, you are very good in general relativity. Okay, so here what I was trying to tell. So general relativity, as you can see, gravitational time dilation, gravitational waves, frame dragging, black holes, all these are very covariant in nature, and remember, they are non-linear in nature. Now, I will explain to you slowly what is covariant. This is coming from the covariant tensor. That means if this is going in this way, for example, this vector, it is moving in this direction. Covariant means this will also move in this direction, maybe a little bit more or less, but this is. Contravariant tells if this is moving direction, it will move in this direction, opposite. Right. So that is why it is telling that gravitational time dilation, etc., are non-linear. That means they do not move in a straight line kind of a physics. And they are covariant in nature. That means we will explain it mathematically. If this moves in this direction, it will move co. Co means what? Company along with that. And here you see, when we are making a shift, that means all the rules of relativity, relativistic effects of special theory of relativity, when it moves or it generalizes, it gets into a curvature of space-time. That means from relativity, we move to geometry, we move from a complete change in mathematics, and also the concept of understanding of coordinates change. Now, here I would like to tell a few words that when we say that coordinates are changing, it does not mean that we do not have coordinates. We definitely have coordinates. But these coordinates are not points, the coordinates are not angles, coordinates are not lines. It is a kind of a topological change. That means, for example, my hand, whatever the lines it will have in a straight line, if I move it, if I curve it, it becomes more generalized. That means, if you look into my one of the lectures called Untangling Topology, where I have spoken about how topology has evolved and what are the concepts of topology and what are the generalization, you will see I have talked that the topology or the entire space is changing. That means coordinates will be there, but the coordinates will be much more generalized. So here is the final thing, that length contraction, all this time dilation, this, which are on the left hand side, which are special theory of relativity, now gets moved into transition from relativity to geometry, that it is moves to tensors, geodesic, parallel transports, etc. Now you might be saying that what is the objective? Why I am telling all those things? Because I want you to make yourself understand, commit yourself mentally and physically, that you are now moving more into a geometrical understanding of physics, not typically mathematics of special relativity. That means you need to gear up yourself with more of understanding of geometry, curvatures, space time, intuitive understanding, etc. Obviously mathematics will be there. So this is a kind of a mental preparation, that how do we go more into geometry moving from relativity. So this is a summary, more of geometry rather than relativity. Primarily deals with geometry as intrinsic nature of space-time, and geometric understanding curvatures, those things. That means all those things, parallel transport, covariant derivative, Christoffel symbols, these are basically are more of a geometric understanding, and you need an intuitive mind, not a purely mathematical mind, to understand these things. So if I move to the second thing, here is a note of caution, that you need to learn and observe geometry. Don't jump directly to the mathematics. You should have the ability to visualize things. You need to conceive abstract ideas. And this is the reason I will tell you that if you go to my differential geometry playlist, you will see that I have made a video called General Relativity and Differential Geometry. Yes, his highness from Ottawa, Canada is joining. Thank you for joining. Intuitive understanding is very important. Yeah. So if you go back to my video on differential geometry and general relativity, I always told, and I have seen in universities, this is a big problem. It is a very big problem. Problem is that most of the teachers, I'm not criticizing, they don't go directly to the mathematics, start solving partial differentials. But that is not the case. The case is that you need to first visualize and get a hold of differential and Euclidean, non-Euclidean geometry. At least you will see in my lectures in differential geometry, I've spoken about a book called From Euclidean to Non-Euclidean Geometry. That means why the things have changed from Euclidean to non-Euclidean geometry, that you need to understand, because the entire structure of general relativity is changing from special relativity to differential geometry. Okay, now we come to what is called a geometry of space-time. What do I mean by that? Let us see into this. Just a second. Yeah, I'm so sorry. Okay, this was the slide, then this was. Okay, I think, so this is the geometry of space-time that we have dealt. There is a transition. Okay. Now we come to the very root of understanding what I was telling, that we need to first understand what is a classical system. And I will be very sorry to be a little bit harsh. I am not mentioning classical system means Newtonian mechanics. No. I want to tell you classical system in a different perspective. I will just show you what. So you see all those people from Newton to Faraday to Maxwell to Einstein, all these things, what they have framed has a set of rules, have a set of principles, and it has got an underlying logic. And it can predict that how the future will be. If I throw the ball on that wall, how it will go, where it will land, and how it will come back. The trajectory we all know. So here is a very, a nice understanding. I've taken this from Leonard Suskind's book. So, for example, what is a system? These are non-relativistic system, a magnet, electric current, whatever, and it does not exchange any matter with its surrounding, and it is not subject to any force whose source is. You remember now, just at the beginning of the our lecture, I told you that we are dealing with a system which has got no external interference. I hope those who are watching Rakesh and others right from the beginning. So this is why we consider a system to be a system when there is no external influence. That means if I take a coin, for example, a head, in a single state system, it will be only head, 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 head. That means it has got no tail. So a mathematical set whose elements label the possibilities. The future, what will be the future of a head only coin? It will be only heads. So it is easy to predict. Now, say for example, if I move from head to tail, right? So in a classical system, systems evolve smoothly. That means there are no discrete jumps. So if I start with the head, I will go to the tail. If I start with the tail, I will come back to the head. And if I start with head and go back, head will only go to head and tail will go back to tail and tail. And if there is another system which evolves with time, right? It is evolving with time. That is called what is called a dynamical system. Now, here comes a very important thing. A system which has only got a head and a tail will go on revolving between head and tail, head and tail. Now, this is again very fundamental to quantum mechanics. Because in a quantum mechanics or a quantum field theory, if you watch my lectures, I have spoken that systems do not evolve like that. Systems evolve very spontaneously. So exactness with classical systems, probability with non-classical. Yes, Joe Basile, I think I'm pronouncing you correctly. Exactness with classical system, probability with non-classical. Yeah, not yeah, you can take it in that way, non-classical system. So what I'm trying to tell is that quantum mechanics, as I told you, once you understand the light, you will understand the darkness. So if I tell you that quantum mechanics, I will show you in a few slides, and quantum field theory, the evolvement of the system is different. Now you see, as I'm teaching you general theory of relativity, I'm teaching you something else also, that is evolvement of a system, which will be easier for you once you go into Schrodinger's equation. Right. So that means that when I'm evolving the system, I need to look at the nature of evolvement. Not that I have got a position momentum, I make a second order partial differential equation, that is fine. But the question is that how am I evolving the system? If I am evolving a system which is not interfered with some outward force, that means it's a classical system. Now, automatically, maybe Joe or His Highness will ask me, what will happen if things starts interacting? Very good question, I would say. Let me come to that part. So I thought I will make it in 30 minutes, but your participation is making it beautiful. Right. So here is something very closely you observe. Now, this has also got relation with reversible and irreversible. Now, say, for example, I'm going from 1 to 2. Okay. I'm going from 2 to 0.3. And there is a way from 3, I can come back to 0.2. Now, this is what is called a reversible deterministic system. That means a person who is from 0.3 knows the past, which is 2. A person who is at 1 knows the future, which is 2. And a person which is at 2 knows the past to be 1 and the future to be 3. Deterministic system, not being intervened with any external, external forces. Now, say for example, suddenly a person appears at point number 2. Hypothetical, let us understand. Suddenly a person arrives at point number 2. Now, if I ask maybe Joe a question, Joe, where were you before that? Joe won't be able to understand. Why? Because there is no past, there is no future. And I have not mentioned over here, but it is good always to mention, this being suddenly at point number 2 is called a spontaneous system. Spontaneous emission. I will come to that anyway. I don't want to confuse with those terms. So if I ask Joe, where were you at point number 1? Where were you when we were point number 2? Joe will say, I don't know. because there is no past, there is no future. This system is called the irreversible system. That means if the cup fall down right from my plate, my wife will be angry, but it can run back to our original system as per the entropy's law or the thermodynamical system. That means there is no state which leads to A. That means it is an irreversible system. And also understand this irreversible system cannot be defined by classical mechanics. Let me repeat it. An irreversible spontaneous system cannot be defined by classical mechanics. That means this is where classical mechanics fails and quantum mechanics takes over. A system which is trying to define this point number 2 cannot be a classical system. It is a system which is far more advanced, and it is called quantum mechanics or quantum field theory, which deals with spontaneous things, and it is an irreversible system. We will come to that. So now you understand that this is what is called a reversible irreversible system. Again, you might have a question, why I am showing you. I will come to that point. Now, if I go to the next part of the slide, you will see this is something which I am trying to explain over my lectures in quantum field theory. There is something which is called a spontaneous emission. What do we mean by spontaneous? If I ask His Highness, tell me what is spontaneous? Spontaneous poet, spontaneous cricketer, spontaneous writer, anything. Now, so spontaneous emission means something which is emitted spontaneously, whatever. It can be atom, it can be electromagnetic radiation, whatever. That means it says that it has a quantized amount of energy. And because the very definition of classical physics tells that it is classical electromagnetism or classical physics is not quantized, that means classical physics assumes that energy can exist in any amount, and it dictates, while quantum physics says that it is energy is quantized. Now you might be wondering why I'm suddenly shifting to quantum mechanics. No, I'm not shifting to an emission for seemingly no cause. Yep. No, not for no cause. I would say it is not for cause. Okay, I will come back to that. It's a good question. Actually, emission takes place from a state of what I would say from an excited state. An atom from an excited state immediately go back to the lower energy state. But the problem is that from this lower energy state, it cannot go back to the higher energy state. Okay, just hold on. I will just give Joe Bailey one link because he has got a wonderful question. So Joe, I will request you to just have a look on this later, and you can understand. It's a very important part for me. Okay, so Joe and those who are watching this, you can watch it later. This actually will speak of spontaneous emission. So you can later look into this. For the time being, what I'm trying to understand, a spontaneous emission actually tells that suddenly, spontaneously, it is being emitted. Okay, now if it is emitted suddenly, classical physics cannot detect it. Classical physics cannot detect it because classical physics is unable to do, because it always has a past and a future. You remember this slide. Let me go back. It will become clear. This one, a past and a future. Like a well can. Yes, that, yeah, absolutely. So the question is that now if Joe is at point number 2, this is spontaneous emission. Don't take me wrong, Joe. I'm just taking casual names to increase the participation. So that means it is not quantized. And in the absence of quantized electromagnetic field, the excited state also cannot go to the ground state. I told you, you see this video, Joe, things will be clear. If you are not, just contact me over my email. I will make you understand. So this will done, and the electromagnetic field is quantized in it. In order to explain this spontaneous things, that is, imagine that it is you are at position number 2 suddenly, quantum field is required because the electromagnetic fields needs to be quantized at every space. That means I have to determine this, all of those. Anyway, these things will become clear. So here is the analogy. This blue electron is going from E2 to E1. But the question is that this is a spontaneous emission, my dear. It cannot go back from E1 back to E2. That is what is the problem of irreversibility. And irreversibility cannot be defined by classical physics. And general relativity is a classical system. So here you see in the green box that the system does not return to its original excited state. The process is irreversible, meaning that the system cannot go back to the original one. And what is a reversible system? Isothermal expansion. Take a cup of coffee, put it on a AC, it will become cold. Take it from the AC and put it on a hot plate, it will again become hot. So don't you think this is an isothermal expansion? That is, it is a reversible system. Okay. So here are three possibilities, one by one. I will explain. First, the left hand side. The atom emits a photon. The photon has many states. This, right? Infinite places it can go. So question is that where will it come back? There is no home because it has got infinite possibilities. Probability number one eliminated. Number two, you see this one, this part. So you see that even if I observe, even if I assume that the photon will come back to its original state in the journey from here to Ottawa, Canada, which maybe His Highness will invite me someday. If I travel from here to Ottawa, I'm so tired, the photon is so tired that it will lose its energy during its journey and it will never go back to the original space. Now, the objective I am showing is that to explain you that why the photon cannot go back to its original state and why it is an irreversible system. Third position on the left hand side, you see that even say hypothetically assume that the photon is emitted and they somehow find its home and goes back to the original state, it is not instantaneous. That means the time when it was emitted, all are welcome to Ottawa. Okay, thank you very much. So the time when it was emitted, and by the time it goes back to its original loop, there is a time gap. And between this time gap, it has met with many friends. I have met with Joe Bailey, His Highness, and a lot of people who are maybe watching me. So if it interacts with matter, it is again very difficult to tell that where actually it has been. So three possibilities are eliminated. In finite ways in electromagnetic emission it happens. It cannot go back because it has got tired. And third is that even if it goes back, there's a time gap, and in between that time it has interacted and it is impossible to find its own way back. This proves us that spontaneous emission is an irreversible process, and that is why classical physics cannot explain it. For example, I was just talking to this. Now you might be wondering, is this a general relativity class? Yes, but I'm coming to that. You see, Schrodinger's equation, the problem was that Schrodinger's equation was failing to describe spontaneous emission. Why? Now comes to the point. I told you right at the beginning that you need to very closely understand how a system evolves. So in a classical system, position, momentum given, and second order partial differential equation, I can tell where it will go. Do you think that it has got any difference with quantum mechanics? Absolutely not. Only in that case we are given position and momentum. Here we are given a probability wave function. Someone was telling, I think Joe was telling, that it is a probability. He is absolutely right. So that means Schrodinger's equation is something like F equals to ma. This is in a macroscopic world, this is in a microscopic world. And because Schrodinger's equation is a classical equation, remember, that is why it is unable to explain spontaneous emission. Because spontaneous emission, once it is emitted, it cannot go back, and it has got infinities and various other problems. So the question is that how will it do? Schrodinger's equation cannot do, because Schrodinger's equation also said, given this, how a wave function, it evolved. That means you can say that the electron is right over that AC or on that switch. A probability, but still that probability is very classical in nature. I hope you're getting my point. That probability is also very classical in nature. So for that, what we required, I have not mentioned here, but again, welcome to Joe. I have given that. You can go and see. That is why we need something which is called a Dirac equation. Paul Adrian Maurice Dirac, a very handsome gentleman, Okay, he made a Dirac equation, which is a relativistic part of Schrodinger's equation. That means it has taken all the special relativity part. I'm not going to explain, otherwise I will keep on talking on that again. Okay, so here we come to what is called a deterministic and not. Now you see that xt and 2 and 4 can determine that where exactly the event is happening. But on the right hand side, you see those red dots. The electron can be there, 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 there. It can be anywhere. And by using Bond's identity, the Max Bond's law, I can square the amplitude. I can say maybe, probably it will be near here, near there. That's it. So this is what is a deterministic and non-deterministic system. So if I square it, you see that I have a probability of finding the particle around this dx area. Are you getting my point? And this led to the famous line of Albert Einstein, which is called God does not play dice. Now, God does not play dice means what? That means it cannot have any probability, because Albert Einstein, by his heart and mind, believed that the nature and its laws are all deterministic in nature. It cannot be that an electron or a subatomic particle, how it is possible that it can be here, 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 or here? No, it is not possible. It has to be at a specific place. And this disturbed Einstein till his last days. And that is the reason he formulated, he made this. This was a letter. I'm just finding out if I can give to all of you this video of mine. It is called God Does Not Play Dice. And yeah, I got it. I got it. So to Joe and others, this would be a good video. Free will versus determinism. Yes, Joe has rightly pointed out. So, Joe, I've just given this link. I have tried to explain the philosophical interpretation of God does not play dice. So, this was the problem. Now, you see, general relativity being a very deterministic part. Why Einstein called God does not play dice? Most of the young students, they make a mistake that no, 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 this is a philosophical or a theological or religious. No, it has nothing to do with that. Okay, so what are the predictions that we get in gen? Now, till now, we have understood that this is a system, how the system evolves, what is a determinist system, what is a non-deterministic system, how spontaneous emission is a irreversible phenomena, and why Schrodinger equation or classical physics cannot define a deterministic system. Here we see few of the predictions of general relativity. You can just take a quick note because I will come to those much later mathematically. One, it says that it has an equivalence principle. That means an experiment that can distinguish between an observer in free fall and in an observer in an accelerated plane. Simple. If I am sitting today on my chair, and if I am sitting on the chair on a lift, if the lift pulls up, I feel a thrust on my back. And here also I'm feeling a thrust. So given a kind of a hypothetical experiment where I cannot see, where I cannot hear the lift sound, I cannot say whether I'm sitting on a lift or I'm sitting on my room. Simple. I will come to those equivalence principle later. Obviously, it has got a curved space-time. We will come to Einstein's field equation as we will explain more. And objects in free fall, in free fall or unaccelerated motion, these are called geodesics. Don't worry about these terms. I will explain them one by one. These are few of the predictions. It also tells that time dilates. That means near strong gravitational fields, time will become longer. A warping of space-time, no absolute, and a geometric nature, it causes a curvature. I'm just showing you for the sake of showing, because these will slowly come one by one more detailed in the upcoming classes. Here it comes. Now take a note. This is how we prove that general relativity is a classical theory. We have seen what is classical theory and quantum theory. Now you see what I'm trying to show. General relativity is a field theory. That means you see on the right hand side those electromagnetism, tensors, and gravitational field. If God does not play if God does play dice, then God's dice is highly deterministic, unlike humans' dice. Yeah, Rakesh has made a very witty comment. Yeah, if God does play dice, then God's dice is highly deterministic. Anyway, so if it is a field where there are given certain initial conditions like electromagnetism, magnetic field, tensors, spin-offs, whatever, the question is that this can be highly deterministic. As you see on the bottom of the screen, I have shown that you're given certain energy, certain conditions. In future, you can predict. Now, here I am coming to a very crucial and important point. In future, I can predict. But again, going to Joe's funny example, if I am at point number 2, I cannot predict the future. So this again brings us to the central point that an irreversible system cannot be defined by classical mechanics or by general relativity. That means we need to have a deterministic system. And due to this determinism, that led to Einstein tell that God does not play dice. Anyway, so if I am given initial conditions, I can predict the future. And this prediction can be done by Einstein's field equation, R mu nu, etc., which we will explain one by one in much detail. That means it proves from today that general relativity is a classical theory. That means there is a lack of inherent probability. That means if I toss a coin, there's an inherent probability what it will lead to, head or tail or head. But there is no probability. There is no inherent probability. There is a difference between probability and inherent probability. Inherent probability means the nature or the quantum particles by what I would say inherently, internally, they are probabilistic. So the behavior of particles are determined by the initial and final conditions, and it can be done through equations. And here you see there is a conservation of information. This means that if we know the complete state of the universe, at one point we can, in principle, predict the future with no loss of information. Here I am coming to the point. If you're joining me on 25th of November's General Relativity, this is something which created a problem. There's a story which is called the Göttingen problem in Germany. When Einstein and Hilbert, they have already published general relativity, they found that the law, spooky action, yeah, absolutely, spooky action at a distance. So they actually found that the law of conservation of energy is violated. Imagine 1915, the general relativity is published, but Einstein found mathematically there is a problem. What to do? Whom to solve? Einstein cannot do it. David Hilbert cannot do it. Felix Klein cannot do it. One lady, one of the greatest woman scientists ever born on this earth, who never got a full professorship, who never got a recognition, neither she got a full-time salary. Can anybody tell the name of that lady on the chat box? I will wait for that. So the thing is that, okay, so we go to the next part. So here you see that general relativity is very predictive and successful because general relativity is deterministic system and it adheres to the principles. We also see that the causality, yes, Rakesh is always right. Emmy Noether. Emmy Noether was the lady, and we will talk about Emmy Noether's symmetry. It's a wonderful theorem. Anyway, thank you, Rakesh. Now see the causality and determinism, what we say as the special theory of relativity is this space-time diagram. Okay, what we say is the future cone, the light cone diagram. So causality is the principle that every event has a cause. When we talk of causality, means every event should have a cause. And determinism means that it is the principle that the future of a system is uniquely determined by its unique current state and the laws of physics. So what we get from here is a quick summary of today's lecture. So we understood today that what is a system, what is general relativity. Is it only relativistic? No, it is not relativistic. It is very much geometric in nature. And general relativity deals with the geometry of space-time. We understood what is a classical system, which is very, very, very central. Most of the teachers and most of the books, they base on this. We also understood what is a deterministic and a non-deterministic system, because by understanding deterministic and non-deterministic system, now we can understand the true nature of quantum mechanics and the true nature of classical mechanics. And we have established through these slides and today's talk that indeed general relativity is a deterministic system, because if you're given certain initial conditions, you can predict the future behavior. But here is my question. Here you see, let me go back to this slide. Here you see that there is no way in which you can predict the future, Because spontaneous emission or any, I have just taken this example, there can be many examples, don't mistake by that. But if the photon is once emitted, it cannot go back. That means there is no way in which we can define here or apply the rules of general relativity in this level. Now you see Rakesh and others, or Joe, who are watching me, today we are struggling to find a theory of everything. Why? Because gravity is not being married to quantum mechanics. We got strong force, we got weak force, we got electroweak unification, we got special relativity, classical mechanics, and quantum mechanics married to what is called Dirac equation or quantum electrodynamics. But today we are in search of gravity, graviton, or string theory, all those things. Now, what is the reason? The reason is this. The reason is that this nature of spontaneous emission is such that classical equations or Einstein's field equation or Newton's laws of motion is unable to detect or tell how it will happen, because classical physics is highly dependent on a deterministic way of physics, and quantum mechanics is dependent on a non-deterministic system. And very few people actually knows this also, that Schrodinger's equation, although it is a relativistic equation, but it is classical in nature. That means it cannot be, describe relativity, special relativity. And once you go to this video, Joe, which I have given to you, you will see that I have explained that why Paul Dirac's equation is relativistic. Because Lorentz transformation, Lorentz invariance, all those factors which are in special theory of relativity are described by Paul Dirac. But the problem today is that we are unable to search the theory of everything, because this scale determines spontaneous, and this classical determinism is time dependent, or we can say it is a reversible system. So in today's class, we have established what is a classical system, how it happens, what are the problems with spontaneous emission, and how what are the predictions of general theory of relativity. So in the next class, which is not happening tomorrow, don't worry. Joe, you understand, I don't know from where you are logging in. So it is 9:45 p.m. Indian Standard Time. You can say 9:50. So you can contact me in my email or in the community. I will put up when I am coming next. Tomorrow it won't happen. Maybe day after tomorrow. I carry on alternating between quantum field theory as well as, based on your reversible and irreversible, can we say our fate or future is deterministic if I found a theory of everything? Okay, this is a very nice question, Rakesh. But the question is that reversible or irreversible is something which determines the fate of ours, but theory of everything is not related by that we want to determine the future. Theory of everything is where in one single equation we can frame all the laws of physics. In one single equation, where electromagnetism already done, special relativity already done, quantum mechanics already done, electroweak force already done, gravity not done. Right? Reversible and irreversible system, we can say fate or future is deterministic, definitely, but it has nothing to do with theory of everything. Theory of everything is something which will create another standard model where there will be one small place which is called graviton. That's it. So I will put up the next lecture on general relativity in the community tab, and I will continue with the quantum field theory. Quantum field theory have very less amount of participation. I understand it is little bit maybe difficult or not interesting. Anyway, so thank you for those who have joined me. I would earnestly request, please put up a comment at this end of today's video in the comment box of the live. And thank you for His Highness for logging in from Ottawa. Thank you, Joe Basail, for logging in. I don't know from where you are, but definitely not from India. And to others who are watching this video, special thanks to Rakesh, who has joined quite early, and others. So I will be back. And the next time we will explore more and more on the mathematics, taking step by step. I hope that this was central, and I hope that this is clear, because this is the very basic foundation based on which no, it is interesting. Quantum field theory, watch it later. Okay, this is the basic building block on which the entire foundation of relativity is built. Thank you very much. We'll wait for your comments. Good night and have a nice day. And may the good Lord bless you with all his blessings, and you have a nice life and a nice learning of physics and mathematics. Thank you very much.